Sound check. Hello. Sound check. All right, sound works. Let me. All right. Hello everyone, and welcome to this week's welcome stream, or I guess the first of this week's welcome stream. So today we will be doing slightly less hardcore stuff than we were doing last time, but tomorrow we will be doing slightly more hardcore stuff than we were doing last time. So maybe these balance themselves out. So I want to spend today sort of cleaning up code a bit. We have some stuff that we have done last time to help us benchmark that we don't need anymore. We have some code that we just need to sort of move out to different source files, because our source file is now like 1,000 lines. It's not that much, but it's not, it could be shorter. And I want to sort of make our lives easier a bit in the future by improving the way how we load shaders. Specifically, right now our C++ code, whenever you want to add some extra argument that you want to pass to the shader, some extra buffer, you have to change the shader code, and then you have to change the C++ code. But C++ code you have to change in 2 places, and I kind of want to only change 1 place, right? But that requires us to parse reflection data out of the SPIRV shaders, which is also what we will be doing today. So let's make a short list of stuff that we think we should do today. So let's see. So I wanna remove the FVF thing that we did last time because we don't need it anymore. I wanted to make the RTX switch runtime, so that if you run on an NVIDIA card, we can just hit a button and switch between 2 different modes of rendering. This will make it easier for us to sort of make sure that both work at the same time. And also this is what you would do. Like, you can't really build a special build of your game for NVIDIA RTX cards, right? So you have to do this switches at runtime. So then I want to move swap chain device and shader stuff to a separate file. And I want to basically refactor a bit shader construction and some other stuff around this, which involves parsing SPIRV. Yeah, we'll see. Maybe we'll do something else. Maybe we will get stuck on the last thing, because parsing SPIRV is a bit hard, and we will not get it done. We shall see. So let's start. I also anyway, we'll see how it goes. So yeah, the first thing is, let's just do some boring stuff. So we had this FVF thing before, where it's like a 3rd mode of rendering that we just implemented to make sure that we are not doing really bad things performance-wise in either path. But we don't really need it anymore, so let's just remove it. This will just clean up the code a bit. And yeah, so this kind of code is the kind of code that we also want to refactor today, because this basically says we have 2 buffers. We want to bind 2 buffers to the shaders. It's really unfortunate that we are spending what is it, like 22 lines of code to bind two buffers to a shader. It should not work like this, but there's a better way to do this. There's a cleaner way to do this, which we will go into. All right, and then we also don't need the shader. Oh, the other thing I wanted to do is see if we can just get hashtag include to work in the shaders, so that we can share the vertex struct and some other stuff among the shaders, different shaders that we have. Yeah, okay, so we don't need this one. We don't need the shader. We don't need this shader. Oh. These guys are again in the wrong folder. That's kind of weird. Oh, the other thing I did is I actually managed to figure out the issues that I had with the GLSL extension. So you can see we now have syntax highlighting in GLSL code. So the trick is you install GLSL language integration. GLSL language integration likes to try to compile your shaders, and it fails at doing so. So you have to disable live compiling here. And also the default color for the built-in variables is really, really, really bright green. So, you know, I changed that. But so we now have syntax highlighting in our shader code, which is nice because this is more pleasant to work with. The syntax highlighting tells us that we have a couple of to-do comments in the shaders as well. All right, anyway, yeah. So let's see if our code works. Oh, I think I was experimenting with, let me swap out. I think right now this is using like a multi-gigabyte file, which will not be fast to parse. Even this is not fast to parse. I think we've broken our code somehow. Let's see. Maybe we will start with shader stuff because, well, yeah, let's start with shader stuff because everything else is more mechanical. And after I remove FEF, we'll start like refactoring shader stuff and parsing SPIRV, and then if we have time, we'll do everything else. Oh my god, so Visual Studio Debugger decided that it's a good time to load the symbols for everything that we are using from the internet, and this is taking forever. They should be cached, but I guess the cache got broken. So what's the problem? Oh, maybe this is weird. Hold on. Okay. What happened here? Our code is now broken. Oh, it's probably... No. Huh. All right. Something's going on. Hold on. didn't even start doing anything interesting, and we've already... Oh! Oops. This was incorrect to remove. Refactoring failed. Create pipeline layout. Right. Incidentally, this code is the code that we will be trying to rework completely today, so it's all good. All right. So that's done. Then we have removed. Visual Studio occasionally adds like blank lines. Yeah, which is not fun because Git doesn't really like blank lines. Day, what date is this? 7? 7. Day 7, remove VF mode, we don't need it anymore. So yeah, let's see how hard it would be for us to sort of dynamically switch between RTX modes. Because I kind of wanted to do this, but maybe we should do this later in the stream. Yes, this should not be too bad. This should not be too bad. So yeah, so let's try to do this. So the way you do things like that is that there's a function of Alken. So I want to basically have a boolean that says like RTX supported, and I also have a boolean that says RTX enabled, right? And RTX supported will be true or false just based on your adapter, and RTX enabled will be able to toggle based on the key press. We aren't really handling any key presses right now, so that's gonna happen, but let's do RTX supported first, right? So the way you query support for extensions in Alken is there is a function called enumerate device 6, enumerate something. I think it's this one. Maybe this one. Why does it want a layer name? So that's slightly confusing. Oops. Oh, this can be null. Okay, that's fine. Yeah. So let's do this. So we have selected the physical device, and then after we've selected the physical device, I forget which, yeah, let's do this. We want to get all of the extensions that are available. So in the usual Alken way, this is how you do these things, right? You get the count first, and then you make a vector of vk extension properties, and then you get all of the extensions, and then once you do so, you should be able to go through the list of extensions and see if there is the one that you want to use, right? So in this case, we have 72 extensions available on this GPU, and one of these guys, this guy, is the mesh shader that we are using, right? So after this, we just need to do something like bool RTX supported is false, and then for every extension, if extension name is equal to vk and v mesh shader, oops, no, then we could break after this, but I guess let's break after this. So now we can know at runtime if the device has support for our extension or not, right? So in this case it's true, and if we run this on Intel adapter, which I still cannot do because Intel still hasn't fixed the bug that I reported, then this thing would be false. And we will not be able to check this today, but hopefully we will not make too many mistakes. By the way, we are doing pretty good on bugs that we've reported. So we've reported so far 1, 2, 3, 4, 5, 6, 7, 8, 9 bugs. Some of this happened on stream, some of this happened off stream. 5 of them are fixed now. The other 2 are hopefully on their way. These are in open source projects, so these would be fixed in Vulkan SDK releases. And there are still 2 bugs in Intel driver. I don't know if Intel is looking into these, but you know, we aren't really running our code on Intel hardware, partially because of one of these bugs, so we can wait. Alright, and now basically we have this RTX supported, so now the first thing we need to do is just replace all of the compile time checks that we have that rely on this guy with that, right? So when we create a device, a physical device, we need to initialize, we need to say we need this extension. So for now, let's just pass this guy through, and then instead of this, I guess we'll use a vector, and then if RTX supported, we will. By the way, we are starting to use, if you haven't noticed, we are starting to use C++11 on stream. So this is C++11 feature, which is convenient because, hey, we just changed the C array to a state vector and we didn't have to change the syntax of initialization. So that's nice. All right, and then change that. So now it should be easy for us to dynamically add extensions to the extension array. Oh, and then the other thing is so I guess this will only be used if RTX supported is true. See below. So if RTX supported boolean is false, then we will still initialize the struct, but we will not use the struct. And if it's true, we will pass this struct to the driver. We covered this last time. For now, let's just pass RTX supported everywhere, and then we will clean that up later. Later today, hopefully. I guess let's do a state vector here as well. And then if RTX supported, then we'll do this. All right, so for now let's pass this everywhere, so here as well. This will change later. Essentially we are temporarily making our code a bit weirder because we have to pass like a bunch of things everywhere, but some of these things we will be able to infer later. So that's done. Let's see, where else do we have an if. So basically that's just, we cannot really load the shader if RTX is not supported because it needs special extensions. And since we want to be able to switch at runtime, we'll have to rename this variable. So this will be our meshlet shader, and it's not really a vertex shader, right? It's a mesh shader. So let's be consistent. And then we'll always load the usual vertex shader. So then we need two mesh pipelines. So we are passing mesh vertex shader right now. So this will be the it's not really, I guess here it's not RTX supported, it's more like use RTX. So let's change this. Or I guess RTX enabled. And here also, because we will be calling this function with false even if we are running on an NVIDIA GPU, because we want to switch stuff at runtime. So yeah, so we need two mesh layouts now. One like this, and then I guess like this. Alright, but this one we only need if right, so that's that. And then we'll need another pipeline. Maybe at some point we'll decide that this was a bad idea, but it seems correct to do this. Alright, so then let's just always do this because, yeah, I mean there's no reason not to do this really. Maybe there is a reason not to do this. Sort of starting to feel like this was a bad idea. Although maybe not. Maybe that's fine. Alright, so then here for now, let's just say that it's the same thing. So if RTX supported, we will use the RTX path. I guess this keeps us honest because this will make sure that the code always compiles, and stuff like that. Which I guess is nice. So when we use the RTX path, we need to use the new layout that we have created. We need this guy to be different now, so let's fold this here, here. So here it's this pipeline. And then we have this stuff. I should look at Visual Studio settings because whatever it's doing by default is tripping me up again. What does this mean? Oh, what? Interesting. Okay, and then we need to destroy the shader module. Meshlet. Let's see, so we need to pass RTX supported here. And we have two warnings that are not actually useful, but let's fix them anyway. Alright. Let's see what we have. So we have a kitten that's rendered with RTX, hopefully. And then we let's temporarily disable the RTX path completely, even if it's supported. So we still can render the kitten, no validation errors, so that's fun. So now I want to be able to switch this at runtime, right? To be able to switch this at runtime, I need to handle a key press. The way you handle key presses in GLFW, unfortunately, is you have to declare a callback. The reason why I say unfortunately is that it's painful to communicate data to this callback. So I guess for now we'll just stick a global boolean somewhere, and let's just initialize this to false. And then when we figure out if RTX is supported or not, let's set the enabled flag to supported flag. So the idea is the supported flag will be true or false based on the device capabilities, and enabled we will switch by pressing a button, right? So then we will replace this check by RTX enabled check, and then we will here we will say RTX is either on or off based on this flag. And now we need to handle the key press. So whenever we create a window, I guess let's just here say that we need to set key callback. And the signature for this is whatever it is. So it's a window, and then for integers. I don't know what they mean. Window, oh, key scan code action mods. Key scan code action mods. Alright. So action can be GLFW key press or press, I think. Yeah, and if we are pressing a button, then if the key was R, then we will toggle RTX state, right? So nothing changes, so we don't know if our code works. To know if our code works, let's do this. Hold on. So here's the cool thing that you can do. I forgot that I can do this on stream last time, but so from last time you may remember that we are working on meshlets. There is a mesh shader that processes one meshlet at a time. Meshlet has an index. What you can do is you can steal a 32-bit hashing function from somewhere. We don't really care what function this is. We need to change it because the types in GLSL are slightly different. It's not a very fast hash function for a GPU, probably, right? But it probably would work. And then let's define some sort of debug boolean, right? And whenever this debug boolean is set, automatic formatting doesn't seem to work very well here. So whenever this is set, we will compute the meshlet hash by hashing the index of the meshlet, which should be mi, and then we will compute the color using just components of this hash. So this is a 32-bit integer, so let's do hash and 255 hash 255 hash 255, and then if debug is enabled, come on, let's just say that all components of the meshlet, all vertices of the meshlet will have the color that's the same, which is the color of the meshlet, right? Oh, and we forgot to enable this, and our shader doesn't compile. What does it want? Oh, I probably need to cast everything to a float, as it were. Oh, and I forgot to divide by 255, so there's that. Still doesn't want to do this. Oh, this is a vector 4. Okay. All right. So now we can see that our key clearly works. So when we render with RTX off, we render without the mesh shader, and then we render with RTX on, we render with the mesh shader. And we have added a flag that allows us to easily visualize where the meshlets are in our mesh, right? So that's great. So now we can switch between RTX modes at runtime. So it's really, really easy to check that both of them work. And if we have a need for debug visualization in the future, we have it. On large meshes, it's kind of hard to read, right? But it works. And we can look at the GPU time. The GPU time is roughly the same. I'm not running the set stable power state program right now, so the GPU clocks fluctuate. Probably. Let's actually check if this is true, because maybe it's the same thing as last time, where for some reason they're fixed. Alright, I don't know. Whenever I do a stream, I start by... Oh, maybe the streaming maybe OBS is doing video recording. I think it's doing it in hardware because I have set it up right now like that. And maybe it's switching the GPU to peak clock for some reason because of that. So that, I guess, would make sense. So in a weird way, whenever we do streaming, we don't have to worry about stable power, stable GPU clock measurements, because they should work without us doing anything. Oh, an update to the GLSL integration is available. I don't think we should install it on stream, because maybe it'll break everything for us. Anyway, so that's good. Let's disable debugging. So now we can switch between RTX modes, and nothing changes on screen, as it should. Our code is slightly uglier, but now we will be able to start refactoring this stuff. So let's commit this. Oh, and let's double check that we don't have any stray RTX defines. I don't think so. I think we are good. Alright, normally I would carefully read the diffs before committing, but let's just YOLO it. Convert if RTX to runtime RTX supported enable booleans. We can now toggle between RTX on off at runtime by pressing R. Also add debug meshlet color visualization. All right. So now that that's done, we can cross something off our list. Oh, my tablet went to sleep again. So we can't quite cross anything off our list. Oh, where's Microsoft Whiteboard? Oof. All right. So what did we do? We removed the FEF and we made an RTX switch runtime. Let's quickly check if includes and shaders just work. I wanna do the 0.3 later because I wanna focus on 0.4 because that is more complex. But let me quickly check if we can just include something from a shader and it just works without us doing anything. So I just basically want to include a mesh H. GL Google include directive. Oh wow. Okay. Wow. This is a weird. Yeah, this is a weird artifact from the days of Open GLSL being compiled not offline but like at runtime. So core GLSL language doesn't have include, which seems like something that should be, if Kronos is serious about GLSL still being the language that people write code in, which they seem to be, I feel like this is something that should change. Like, there's no reason to, yeah. Anyway, so basically all I want is I want to move the structs that we have, because the structs define the data layout on the C++ side, so these have to be in sync. So I just want to move them to a header. And then we don't need the struct. All right. And then the other thing is that here we need the same extension. And then I want to include mesh H. And then I don't need this struct. And I don't need this struct. All right, and the big thing that it's doing for us is that it makes sure that if we have another mesh shader or if we have another thing that wants to write or read the same meshlet structure or vertex structure, it's just there. At some point we may start extracting like this hash function. Well, this hash function isn't very good, but if isn't very fast, I should say. But if there is a better, faster hash function, maybe we can put it in some common header. Maybe some of these extensions can go in a common header, because it's weird to keep requiring everything. I don't know if we need this even because we're using Vulkan 1.1, so maybe some of the stuff can be cleaner, but it's nice to know that at least includes work with an extension. Okay. Yeah, so let's submit that and start working on the actual real thing that will take basically the rest of the stream. Move shared structs to shader include, which is improving the way how we sort of reducing the amount of code that we need to write or change when we work with shaders and pass things to the shaders. What should we start with? So I guess let's start from the shader layout stuff. Oh no, I guess, yeah, let's start by moving things to a separate source file and reading the chat. Sasha wrote something and then I can't read it anymore. Alright. Maybe it was telling me that I have a bug that I already have fixed. Alright. Yeah, so let's first move some things to separate source files that relate to the shader work that we are now doing, and then it will be clear what we need to do next. So let's create a CPP file for some shader functions. Let's create source file. Maybe we should have called these shaders instead of shader. Hope you can rename. Yeah. So the first idea is let's just get every function that we are calling, just move it out of our main file. So create pipeline layout. Oops. Should go. Oh, the struct can move somewhere, but it's fine because we are moving this code out. Create graphics pipeline should move. Yeah, okay, now we can take our vertex struct and move it closer to the mesh structure. I guess here would be more appropriate. There was also some function that loaded the shader. Yeah, this one. We'll move that. Alright, that's good enough for now. And then we'll need to include some things. Oh, I guess the lib. Insert. Is this Stadio? Stadio. Oh, we also need our Alken check macro. Alright, for now, let's just repeat this here. We'll make it, or yeah. For now, let's just move this here. And then we need a vector. Alright, and then to be able to call these guys, let's just move them here, here. So our long-term plan for this stream is to remove this boolean, but for now we will keep this boolean. Oh, and I have to include basically Alken headers basically everywhere, right? Yeah, because I'm using Alken structures. Some of these things are forward declarable, but it's not easy for some of them, depending on like the bitness of your application, things like that. It's complicated. So yeah, let's just for now just make a common header that we will assume. It's interesting that Visual Studio, by the way, doesn't compile the headers separately to make sure that they're self-contained. It's interesting that it even knows we're not including this anywhere yet. Anyway, yeah, so I guess for now let us include this header everywhere, and then we can figure out if this was the right thing to do or not. And we will include this here. Don't need this anymore. Don't need this. Should probably also include assert because the chances of us not using an assertion in one of the source files is slim. And let's make sure that this is the first thing that we include everywhere. All right. Okay. Visual Studio has figured out that these are now fine. So yeah, for now we'll make a simplifying assumption that we don't need to include Valcon headers in every single header. It's just part of common. And we should do, yeah, this is fine. So then, all right, so then now we just moved the files around. So here's what I want to do. So the first thing I want to do is that when we the first thing I want to do is I want to switch to descriptor templates, because that would simplify the code in our main program, where right now to specify data to the shader you have to fill these crazy structures, and this is completely redundant because like there is no, like this structure doesn't really change. It's fixed for every, the way we are doing things right now, the structure is fixed for every single pipeline. It's basically the same thing that we were doing when we were filling the pipeline layout. It's the same thing. So what I want to do is I want to switch to using descriptor templates. Descriptor templates are now part of Alken 1.1, so we shouldn't need to enable any extensions or anything like that, but you can use them in Alken 1.0. And what this is we can create a structure called vk descriptor templates, descriptor update template. Yeah. And then if we had that, we could use, instead of push descriptor set, we could use push descriptor set with template. And then we would pass the template. I guess template is a bad word because it's a keyword. And then we would need the layout. Oh, we would need, yeah, I guess that makes sense. Set, and then descriptors. But instead of descriptors, so here's what descriptor update templates do. They say when you pass descriptor data to the driver, you have to specify for each descriptor what the type is, what the binding is in the shader that this should refer to, how many descriptors do you have, what the type is, and the pointer to the actual data. Descriptor update template says, well, if you always use the same arrangement of descriptors in the same call, then you can make a template object that bakes all of this data inside the template object. And instead of this, it just bakes an offset into some data blob, some opaque data blob. And then this is the data blob that you pass here. And then the driver will read these objects from the offsets into the data blob. And then all of this other stuff will be baked in. This simplifies the calling code. This means we won't need any of this code. And we will make this code slightly simpler. And also this means that you don't need, like the driver can save some time by pre-converting some of these enums into hardware-specific offsets, or whatever the driver wants to do, it can do. So what I want is, and whenever you do an update, like this, there's really only, I mean, except for this guy, which we don't plan to use anytime soon, there's these two structs that you may want to use. And these two structs, what I want to do is I want to just say that when you bind like a set of descriptors to a shader, you can just have an array of objects where each object is either this guy or this guy. And this will be really easy to specify in the C++ code. So what I want is I want a struct which we will call descriptor info, that internally will contain a union of this or this. Oh, I should I'm thinking I should have committed the file split first. But fine, let me finish explaining and then I'll commit, right? So I want this struct, and then once you have this struct, you would be able to initialize an array of these structures, and we may want to write some constructor or something like this for this in C++ code, and then just pass the array of these structures to this template update function. And as long as the types of the descriptors match and the order of them matches the order in the shader, we should be good. And we won't need to do any work other than that. So this code would simplify to like 2 lines of code. Most of this stuff will be done. So that will be nice. However, before getting to the state where things are nice, let's get to the state where things compile. In fact, we could leave this for now. But yeah, let's get to the state where things compile and run, and then we'll submit the file split, because then it will be easier for us to see diffs going forward. Oh, and I can switch between RTX. All right. So yeah, so the long term, so what I want to do is I want to be able to say descriptor info, descriptors, and the first descriptor is a buffer, so it should have like VB buffer 0 size, and then the second descriptor should be a buffer, so it should be, so I want code like this, more or less, to work, right? So this code clearly doesn't work because it doesn't know which structure you want to initialize. How are we gonna solve this? If this was like C99, then you would probably be able to use C struct, like designated initializers in some way. But this is not that. Maybe this should just be, let's see. Yeah, you know what, let's just make a constructor. It seems fine. So we'll create a constructor that you can use for samplers, and we're not using textures at all right now, right? But we will definitely need to do that at some point. We may write some code today that we don't really know if it works, because we don't really have a way to test this, but one day we will support textures, right? And then the second constructor will be used for buffers. So buffer offset range. This probably, I forget if VK whole size works on the descriptors, but if it does, that would be nice, because then we can just simplify this so that we can make like a third constructor, which is just a buffer. Let's see if VK whole size works. So this is a barrier. Maybe I should just look at this struct, but I suspect it might not work. I don't know. Oh no, okay, it does work. All right, yeah. So here we will say buffer, well, buffer offset is offset, buffer range is range, and we'll make a third constructor which just takes a buffer and binds the entire buffer. And you know, like, we can make another constructor for images because some of these guys can be null in some cases. Here's the nice thing, by the way. I think these structs, these two structs are the same size, so we aren't even wasting any memory on this union. It's like the same thing, because I think basically these are 64 bits, all of them, and these two are 64 bits, and this is 32 bits, but there is 4-byte padding after this, so they should even be the same size. Anyway, and after this, I will be able to just say, hey, I want to bind two buffers, and this will use the implicit C++ like conversion, because it will pick basically this constructor implicitly, which is actually nice in this case. And then I can just pass this guy to this function, and then this code goes away, and this code goes away, and this is like super simple. So this is what I want, right? So now that we think we will be able to use this once we create a template, let's commit stuff, because we need to add basically a bunch of files. Also descriptor info that we can later use for templates. Alright, so to prove that this idea works, we need to create a template, and right now we the template should match the pipeline layout, in the sense that since pipeline layout right now says there is for RTX path, there is one descriptor for for vertex data and one descriptor for meshlet data, it's kind of the same information. So because of this, for now, we will just also do this same hard-coded thing where in C++ code, we will hard-code the structure of the template. And then once that works, we will be able to automatically infer the structure from what the shader needs. vk update template, descriptor update template, create update template. It's technically descriptor update template, but this is such a long word. It seems like update template is fine. All right, so this function should be straightforward as usual. So we need descriptor update template, and I can't call this template now. Okay, update template, vk create descriptor update template, so device, create info, allocator, and then update template, and then there is vk check here, and then return update template. So that's all the usual thing, right? And then we need vk descriptor update template create info, vk structure type descriptor. Oh god, if IntelliSense didn't exist, this stuff would be even more painful. So let's see. Oh, and we'll need to pass a pipeline layout and some other stuff here. So we need to fill the structure. Let's see what we need. So these flags are future extensions. So let's pass vk pipeline bind point, I guess. Vk pipeline layout. And then we aren't really using sets at all right now, but let's just, it doesn't, well, we will use sets in the future, but it might not be actually used with this function ever. For now, let's just ignore this. But we do need compute support in the future, so we do need to be able to say we need this template for a compute pipeline instead of graphics pipeline. So yeah, so this is our actual signature of this function. Right, so let's see, what do we need to fill? Oh, we need descriptor set layout, which happens to be the exact same thing that we were constructing here and destroying here. That's fine for now. Let's do the same thing. It's slightly weird. Oh, okay, yeah, okay, that's fine. Let's move some of this code. Create basically set layout. So this was the actual thing that was hard coded. So we'll move this here. I still don't know the answer to this question. Is it safe to destroy the set layout just like that? Especially when it relates to this. But for now, let's assume it's safe, because, you know, validation layers didn't say anything. So it might be safe, but I haven't looked. I should actually look at if this is safe. And if it's not, then validation layers should really check this. Alright, so yeah, so we need the set layout in the same fashion. We, in the same fashion, will destroy it here. And then there's a template type. I don't know what this is. Yeah, so this is saying, are you gonna use this template for Vulkan core descriptor set update or for push descriptors? Right now we are only using push descriptors, so let's hard code this. This might need to change later, but who knows? It's possible that for, like, the only reason why I want to use the non-push descriptors is when we start doing textures, I will want a giant descriptor that has like 1,000 texture descriptors in it, giant descriptor set that has 1,000 texture descriptors in it. But we don't. Yeah, this is fine for now. All right, and then we need these entries that basically should map for each descriptor in the shader. We need an entry like this that basically has the exact same information that we were filling before. And right now we'll have to hard code this information because we aren't parsing SPIRV yet. So right now we will have to do entries to the vector, and then if RTX is enabled, then we need a moral equivalent of this thing. Otherwise we need a moral equivalent of this thing. And it may seem like we are just sort of moving hard-coded bits of code around in the wrong place, but the idea is all of the hard-coded things inside this file, they can be inferred from the shader bytecode, which we'll try to get to if this stuff works quickly. So we need 2 here, we need 1 here, and then most of this stuff, I think, is just descriptors, entries. So let's see, so DST binding, DST array element, descriptor count, descriptor type, offset. Stride. Oh, stride is used for arrays, right? So this will basically be size of descriptor info times 0, because this is the first descriptor, and then so I'm just making an assumption basically that if the shader references descriptors like 0 and 1, then they are sequential in our input buffer. Oh, and we need the stride, which we don't need right now because we don't use arrays, but might need in the future. And this is like that, right? And I think we basically need the same setup here. All right. Now we need to pass this. Oh, we are not calling this function, so everything works for now. Alright, so now we should be able to create this template after we create the pipeline layout. So vk descriptor update template, mesh update template. No, wait, I want our function. Oh, we called it create update template, right? Device vk pipeline endpoint graphics, and then mesh layout, and then RTX enabled is false. And here we'll be able to do descriptor update. Mesh update template RTX. All right, and finally, we can take all of this code and remove it, because what we want is we want to say descriptor in for descriptors. We have two descriptors, one binds a vertex buffer, one binds a meshlet buffer. And then remove all of this code. And then we say we want to use the mesh update template RTX and mesh layout RTX and then descriptors, and that's it. Why not? Why is that not it? Wait. Oh, I need to. Okay, yeah, that's fine. And then here we say, hey, we only have vertex buffer. And in theory, we can extend this to uniform buffers and to images, and like it's just if we correctly fill the template, then it should just work, right? So this is way simpler, and this should also be faster if the driver is good at doing what it should do. All right, vk pipeline uses set 0, but that set is not bound. Is that so? How should I put this? So, okay, the code that we have written works, but oh well, will we actually get to SPIRV parsing today is the question. So we are getting a validation error. Let me first. So right now we are enabling RTX path if it is supported. Let's start with disabling RTX path and see what happens. No, it's still broken. Okay, all right. Let's see what happens here. So we did a push with a template that specified the buffer and layout and all of that stuff, and we are getting a validation error that says that pipeline uses set 0, but that set is not bound. So it looks like when we switch to templates here, the validation error started triggering because it thinks that we aren't binding set 0, even though we seem to be. I wonder if there is some order dependency. So at this point, there's two usual possibilities. It could be a validation bug, or it could be our bug, and it's hard to know. So yeah, so one possibility is that the validation layers, when you use this function, they don't track the fact that we have just bound set number 0. The other possibility is that we are not doing some setup correctly and something blows up. Another possibility is that this is actually not safe to destroy, and this will be a memory leak, but no, so that is inconsequential. Yeah. Okay. Okay. All right. So. Damn it. I was trying to work here. So let's do the sensible thing and read validation layer source code to, if it looks like they just don't do the thing that they should be doing at all, then this probably is a bug in their code, right? If it looks like they are doing the thing that they're trying to do, then maybe it's a bug in our code. Fortunately, I'm not an expert on validation layer source code. And we didn't start doing SPIRV parsing. Should we just ignore this error and parse some SPIRV and then like offline? Like honestly, given this, like I have seen many sort of validation issues around the push descriptor stuff, but so far they have been in the land of the validation is incomplete, not in the land of it just doesn't work, which might mean that it is a bug in our code, because who knows? Where is this function even declared? So when we use the non-template function, it validates like the objects are correct, and then it's calling this validate descriptor right function, which I'm assuming does some sort of tracking. Let's see if that's true. No, probably not. All right, let's look at the code that actually generates this error. That might be easier. Yeah, okay, cool. So it looks at bound descriptor sets and says that bound descriptor sets is empty. So we need to look at the code that updates this set, and also we need to switch our search mask to like CPP files. Okay. So it sort of looks like no, this will not. So maybe this function updates, but it shouldn't be this function, it should be some other function. Alright, you know what? If the set wasn't bound, nothing would render. So I feel like let's do a sanity check on our creation of the template. But honestly, I feel like we have found enough. I was really worried we wouldn't find any bugs today, because you know we would be parsing SPIRV, and it's kind of baked. Like you can't really find bugs in that. Like you can find things that you don't like about SPIRV, or you can find bugs in GL slang, but we already have found all of the bugs in GL slang that we could with our shader. Yeah, so when we create, we say set 0, it's not like uninitialized or anything, right? And then we have one descriptor, which goes into binding 0, array element 0, one descriptor, storage buffer, offset 0, stride 24, which is the size of our structure, 3 8-byte entities, right? So honestly, I mean, I'm like 99% sure we are doing everything correct. And validation layers just did not do their job, like they don't track things, you know. Anyway, so that's my assumption. I will file, not find, we already found the bug. Now we need to file the bug. I will file the bug off stream to not spend time on this, because we have 40-ish minutes left. I kind of wanted to get to the SPIRV stuff, but so that this doesn't block us, we'll do the same thing that we did here. This bug has been fixed, by the way, but we are using the SDK before this fix, so we still need this workaround. So let's just say, hey, sorry guys, validation layers are broken again, and we will work around this the exact same way. In theory, we may be able to use, like, this thing is actually retrievable as an enum, but honestly, what does it matter? Basically, let's say that, and this is dangerous because this can be a legit error. Like if we did not bind anything at all, this would have been a bug on our side, right? So it's dangerous to ignore this, but don't correctly track set assignments when using push descriptors with update templates. Bug to be filed. Just out of curiosity, let's check if somebody has already graciously reported the exact same issue. I forget what the repository is named. Alken validation layers. Push descriptors update template issues. So that's the bug that we filed. Oh, hey. Is that our problem? With push template. Yes. Yes. Alright, so this is our bug. Awesome. We don't need to file this bug, but we have hit this bug. Yeah, so it doesn't update the state that the VU test relies upon. I'm hitting the same error. I don't think the status... So the problem is the status is incomplete. It should not be incomplete. This is like a... Oh. Yeah, so incomplete is missing validation check. The problem here isn't that it's a missing validation check. It's that the validation error is happening for valid code, which is way worse. That's correct. It should not be incomplete, as that indicates missing validation. The status quo is that trying to use update templates with push descriptors generates an error in otherwise valid code. I feel like this should be a bug, and the priority should be, well, you know, a relatively high priority bug. Well, who knows? But like incomplete basically means, hey, validation layers could be nicer and could detect errors that they don't right now, but it's very, very different from bug, right? So there is that. We will, you know, let's just whatever the title of this is. Alright, hey, at least we didn't spend like 20 minutes debugging validation layers and then finding out that this is a bug and then filing the bug and then the bug is already known. Okay, alright. So I'm glad that's past us. Alright. Oh, right, yes. Now we also need to delete the objects that we have just created in the first place. Alright, so that's good. We have switched almost successfully to descriptor update templates. This will help us long term. This also helps us short term. Oh, we also don't want to commit this. Day 7, switch to descriptor update templates. This makes our draw setup code much shorter and likely faster. I have actually measured descriptor update templates, but not with push descriptors, but I have measured them a few months ago, and they were faster on NVIDIA for sure. They were slower on AMD because AMD driver was really suboptimal there. I heard this has improved since in AMD driver. And I forget what Intel results were. Well, the Intel results were that it was a bug that prevented me from testing the performance, but they have fixed the bug since. I don't know if it's faster on Intel or not. But like, descriptor update templates are nice for some workloads. Like when you actually update descriptors, it's nice to use a template. With a well-written driver, it can be faster. And likely faster. We have also hit another validation bug that has been reported before, so we have to ignore this error in debug callback for the time being. As is common for this stream, you know, probably not surprised, we use relatively new features. We use Alken 1.1, we use a bunch of extensions, so we hit bugs. It is not entirely surprising that this is happening. Alright. Still don't know the answer to this, and we are now also creating the set layout redundantly, but that's fine. Okay, so now we need to start parsing SPIRV. I don't know if we will make it today, but we will try to get somewhere. We'll see what that means. Like, we'll see how far we can get. There's an intermediate step we could make. Oh no, yeah, right, so here we have to declare all of this stuff anyway. Yeah, basically we just need to do the full thing. Basically we just need to do the full thing. Okay. I'm trying to figure out how to best start this. This stuff is bound to pass, which might be fine. Yeah, there's no way we'll make it. There's no way we'll get to a complete like SPIRV parser today. Well, we can try. Anyway, so SPIRV parsing. So here's our next step. So this code isn't terrible, but here's the bad thing about this code. We have to pass this boolean everywhere, and inside these functions, we are hard coding the essentially setup for our demo, right? Like when we use RTX, we use a mesh shader that reads data from a storage buffer and from another storage buffer, but fragment shader reads no data, right? When we don't use a mesh shader, we have a vertex shader instead of a mesh shader, but it still uses a storage buffer, but only one, right? All of this stuff I want to completely infer from, like this entire file should not contain any information about the demo. Now, right now, like there's this stuff, right? Like right now, it also contains some state setup that we might want to change later, but these guys are less bad because they will just migrate to parameters to this function in some form, right? But all of this other things that are hard-coded right now should go away. Because right now, if I want to like add another storage buffer, I have to change this code and shader code and C++ code in our main program, and I don't want to be doing that. So that all has to go. That all has to go. This swap chain device stuff bothers me as well. I really want to move that, but that'll take whatever. So yeah, let's see how we are doing on stuff that we have wanted to do. Can I just cross things over from this without a pen? So we have moved shader. We have done including shaders. We have done something here that moves us to the bright future. So we refactored a bit of code, like, but we still need to parse SPIRV. No, we didn't move swap chain. Let me move swap chain code. I'll leave device code, but swap chain is already nicely organized into functions. Let me just move this because it bothers me a bit. And then we will proceed with the parsing. The parsing will commence. So swap chain. What is it doing? No. No, I didn't want this. I wanted a CPP file. Alright, so let's just take this struct, move this here. No, not here, here. Oh, the other thing that we should include in common.h, or I guess Valken.h includes it for us, but basically we should also include student.h, because oh, and we are including vector. That's yeah, that's fine. Alright, so let's just take all of the swap chain stuff, create, destroy, resize. Oh, there's not that much. Come on. And then move that. Okay. Oh yeah, there is some other function. Oh, and there's also get swap chain format. So that is just some internal function, I think. So this could be okay. But we now need to create image view. And create frame buffer. All right, you know what? This was a bad idea. This is why I was committing things after each substep. It would be nice to move swap chain functions, but they rely on some of the render pass stuff, and that's harder to move because we might want to use it elsewhere, and we'll just create problems for ourselves. All right, let us just focus on SPIRV. So here's what we are doing. If you look at our shader right now, at the mesh shader, say, right, then it says, hey, I want to use a buffer that's bound to the slot 0, and I want to use a buffer that's bound to the slot 1, and I want to parse this information out of the SPIRV file, so that when you create a shader pipeline from like a mesh shader and a fragment shader, we know that mesh shader uses, you know, binding 0, and then fragment shader uses binding 1, and we just know all of these things ahead of time. Or not ahead of time, but we already know these things ahead of time, but right now we are hard coding this in C++ code, and I don't want to be doing that. So to get that to work, we need to look at SPIRV file and to extract reflection information out of this. Specifically, for example, if we were to look at the mesh shader, meshlet, we can disassemble it, and there's a lot of instructions here, right? But also there's things in the beginning of the SPIRV blob that declare the resources that the shader uses, the extensions, etc. This is a text disassembly. Obviously, the SPIRV file is not a text file. It's a binary file. It looks like this, right? So we need to load, when we load this file, right now we already do so, but we don't look at the contents at all. So we need to start looking at these contents and interpret it in a way that will let us discover these bindings, and then save this data, and then when we create the pipeline, use this data to make things just work, right? We can also infer, we should also be able to infer from the shader what type of the shader it is. Like here it says op entry point mesh NV, which means it's a mesh shader probably. If you look at our vertex shader, then it says op entry point vertex, which means it's a vertex shader, right? So we can infer a lot of stuff from the SPIRV code. Now, under normal circumstances, you would be using projects that help you deal with that. For example, there is a SPIRV cross library that you can use for this. We use this library at Roblox offline. We don't have reflection at runtime, but we do use this offline. This library is kind of large. It does some other things. It's not terribly large, but it's like not just reflection library. There's another library that you may want to use, which is SPIRV reflect, which is a lightweight library, so it only has reflection code. However, even this library is, let's see, 4,000 lines of code. And we could just integrate this library and call it a day. But, you know, remember, we are trying to not use third-party libraries that help us write Alken code. We are using third-party libraries that help us with non-Alken things, like mesh loading and whatnot, right? Math library in the future. We also made a special exception for Volk Because writing an extension loader on stream when I have already written an extension loader seems just pointless. Plus this code there's like 1,000 lines of code here, but they are all really boring, right? There is nothing here. There's nothing interesting in this code, which is sort of the point. It's a library, you include the library and you don't have to write boring code. Well, I mean, there's like 20 lines of non-boring code at the beginning, right? Comparatively in this library there's like 4,000 lines of code, but all of this code hopefully is meaningful, as in it actually parses stuff out of the SPIRV blob. It's just that it parses everything that you can possibly want out of the SPIRV blob, and we don't want that. We just want very few things. So hopefully we can spend like 100 lines of code or so and parse out all of only the stuff that we need, because we still want some contracts to hold between our C++ code and shader code, like the structure layout should be the same, but we just want to figure out the resource bindings and the shader types automatically. So yeah, so that's the plan, and we don't have a lot of time left, so I don't know how far we can go, but I want to spend at least like half an hour sort of doing this stuff, and we'll see. So the first thing that we'll do is we will make a struct for a shader where we'll parse the shader module, but we'll also parse other stuff. So let's change this to this signature, and also when we create a graphics pipeline, yeah, that's fine. For now, we'll keep passing things like that, right? But we want more things. So for example, the first thing that I want to do is we use RTX enabled boolean in this function for only one purpose. We want to parse the shader stage out of the shader. So I kind of want to like just know this when we load the shader. So that's the first thing that we do, that we definitely should be able to do. And then the second thing that I want is reflection data. That will take a bit more time, so who knows if we'll get there. But that's the idea. So yeah, so let's add a struct. Pass a struct instead of the Vulkan shader object into this function. And then for now, just load shader. And we could be doing something sneaky, like if path ends in .mesh.spv, then it's probably a mesh shader, but I don't want to be doing that. Shader result module, shader module, and then result stage. We don't know what to fill this with yet, so there's that. And then let's add error handling while we are at it. If we can't load the file, we shouldn't. No. We might want to do more error handling here whenever there's assertions, but for now it's fine. We could add error handling here as well, but that means that the SPIRV blob is invalid, so maybe for now let's just add like a really simple error handling here. All right. If we wanted to use geometry shaders in the future, we would need 3 shaders as an input, vertex, geometry, fragment. But since we are using mesh shaders, I don't think we'll be really using geometry shaders on the stream at all. I'm not a fan of geometry shaders, so why bother? Okay. And then let's change our C++ code. So this will be shader. Let's actually, yeah. I can't just write like a cert load shader because that would be compiled out potentially. We're not compiling assertions out right now, but this makes it painful to write this kind of code, right? Maybe there should be like a different macro that's not compiled out. Alright, so yeah, this is, I guess, mostly it for this refactor. Yeah, we already used the boolean rc, of course, somewhere else, or yeah, we use int rc somewhere. I don't know. C++ is slightly depressing sometimes. There are simple things that could be just part of the language, but they aren't, or, you know, like we could just add a macro for this, but yeah, okay. Right, and then let's do, I don't know if we need to wrap this like this, but I think we've done this with swap chain and buffers and some other stuff. And I don't anticipate having to do anything more than just vk destroy shader module here, but it's nice to have this for symmetry. And maybe it should be called create shader, but I guess load shader is fine. Destroy shader mesh device. And in C++, you may want to use AII, but I definitely don't want to use AII. So it should be fine like this. Alright, what are we hitting again? Oh, did we not? Oh, oops. Yeah. Okay. Alright, cool. So, first order of business, let's figure out what type the shader is. Like what stage the shader is, just looking at the SPIRV blob. So, to do that, we need to look at the shader blob and parse this op entry point statement out of this. Now, to do that, we need to parse the SPIRV file. So we are already loading the SPIRV file into memory, and the SPIRV file is a bunch of unsigned, like 32-bit unsigned integers, but they have semantics that is potentially complicated, right? So I haven't done this before. I have a SPIRV spec here with me. Let's try to, I have a general idea, but not a very concrete idea. So yeah, so SPIRV module is a single linear stream of words. A word is a 32-bit integer, but can I go back? Okay. So first there's the header, which is 6 words. There's like version of the SPIRV, some magic number, ID bound, and some other. Oh, actually, there's only 4 words. So there's 4 words for the header, 5, 0, 1, 2, 3, 4, right? And then the instruction stream starts. So every single thing basically on SPIRV is an instruction. Like this op entry point is an instruction. It doesn't compute anything, but it declares things. So an instruction starts with a 32-bit integer, where the 16 high order bits are the number of words in the instruction, which means that it should be trivial for us to parse everything regardless of the type of the opcode, and then only look at specific opcode. So let's try to do that. So let's do, yeah, parse shader. Yeah, let's just like add a function parse shader where we will give it SPIRV and code size, or like code and code size. And code size was in bytes in Alken, but it's really weird, so we will note this needs to be a number of bytes for unfathomable reason. And then I guess we'll just fill the shader struct with data, right? Let's do this. Oh, all right. So yeah, so the and the other thing is we need to include a header with the some SPIRV structures. I think there was one in Alken SDK, SPIRV H, I guess. I have never looked at this header, so I don't know what it has, but I'm hoping it has like structures or enums or something. I guess it wouldn't have structures, but it does have enums. For example, SPV op. Oh yeah, so SPV op execution model mode. Wait. So right, so it has this execution model, which I guess is the first argument of the entry point, which is the enum that we can look at and directly convert to, hey, it's a mesh shader. So that's good. Word 0 is a magic number. So let's assert that code 0 is there like, let's see, SPV magic number, right? SPV magic number. We will not be doing real error handling, but we'll assert some things. So there is a version, let's just ignore that, generate a magic number, ignore that. So there is the bound, which might be nice. Code 0, 1, 2, 3. This is the, this might be useful once we start parsing some other things, because it's the maximum number of internal IDs in the SPIRV blob, and internal IDs are used to cross-reference every single thing. So like you want to parse a type out of SPIRV, type is an ID that has an instruction that sets it up to mean certain things. So that's useful. So this one is 0, so I guess it doesn't matter too much, and then the real start is 5, right? So then instruction is code plus 5. And then while instruction is not equal to code plus code size, we will parse the first word, which has as the high order bits, it has the word count, right? And the low order bits are the opcode. So opcode should be instruction. The cast is kind of redundant, so it's just this basically, but it's fine. And then word count is that, right? Yeah. And then to skip the instruction, we should be able to, I don't know if word count includes the, oh yeah, it says 0 word count minus 1. Yeah, so we should be able to just do this. And then let's assert that instruction plus word count is less than. less than or equal to code plus code size. So in theory, this parses the entire stream, and this should be const. And then here we can do a switch opcode. And for example, we are interested in SPV op entry point. And then hopefully here, usually do it like this, we should be able to look at the next word of the instruction, which should be probably execution model. So I'm guessing that it's like execution model is instruction 1. Actually, yeah, let's do, this is nicer. And then here we will do shader stages, convert like get shader stage SPV op execution mode, not model. No, wait, hold on. No, model. Yes, SPV execution model. So I mean, it's basically this, right? And then we'll add a function called static vk shader stage flags, so flag bits get shader stage SPV execution model. So we are only supporting some of these, so we don't really need to parse all of these out. Remember, we are not trying to write a general purpose. I don't know if compute is compute or kernel. Kernel is weird. Why does compute say GL compute? I'm fuzzy on this. I feel like, so let's ignore compute for now. We'll come back to this when we need. Ignore RTX stuff, but basically parse this out. And then unsupported execution model. And then here we'll return. It doesn't like the fact that, yeah, like what can I do? Shader stage vertex. So we are using vertex fragment and mesh shaders right now. We are not using task shaders, but we will do this tomorrow, hopefully. I don't think we can get to do everything that I wanted to do today, so that'll spill over to tomorrow, and hopefully not many things spill over after this. But yeah, so this is hopefully how it works, and then we can, in our create graphics pipeline function, we can remove this boolean, and we can just, you know, get the stage from the shaders, and fragment shader stage probably should be shader stage vertex bit, or vs stage is vk shader stage mesh bit, and then fragment shader stage probably should be fragment shader. But the good news is we can use our load shader function now to parse compute shaders and task shaders and goodness. Oh, in fact, right, when we do task shaders, we'll have to have a variant of this function that actually can compile 3 shaders, not 2 shaders. At which point we'll have to pass an array of things, and these asserts will go away. So these asserts aren't even interesting. Let's remove them for now. Well, let's keep them, and then if our code works, we'll remove them. Oh, and yeah, the boolean is no longer necessary here. No, and create graphics pipeline. So now we can just pass them. Well, if the code works, which probably it doesn't, but we can pass. Oh. So our SPIRV parser worked the first time. This is nice. I mean, we are only parsing stage out, but let's set a breakpoint here to make sure that we are not crazy. So here's an entry point. It has 11 words in it, and this is the which shader is this? This is the mesh shader, so it's more complex. So let's look at the mesh shader. No, mesh shader. No. Oh, wrong folder. All right. Yeah, so as you can see, this is the entry point. So it has 1, 2, 3, 4, 5, 6, 7, 8, 9 arguments inside this guy, but the instruction encoding may have more data in it than that. And also there's the first word, right? So there's like, oh wait, let's do this again. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, so there's 9 arguments, and then there's one header, so this is 10. The number of words is 11, so I guess there's one more for some inexplicable reason. Alright, so this went well. Now we have made the create graphics pipeline function nicer. In fact, I'm like wondering idly, can I do yeah, that's fine, whatever. We'll deal with this later. So the second thing that I want is I want to parse out storage buffer stuff. Storage buffer stuff is harder to parse out because you have to cross-reference a few things to sort of to do this well, to do this right. However, we can set up some things for us to be able to do them well later and slightly hack things together for now. And then we can end the stream. We are 2 hours in, but we can write code for like 10-15 more minutes to get us going, to get us mostly there basically. And then maybe we can't. Yeah. Okay. Alright, so here's the thought. Let's do something really simple for now. For now, let's just say that we support up to 32 storage buffers, and then we'll assume that all of the resources are storage buffers, and then that we'll assume that we don't use arrays or images or anything, and it's just like super simple thing to sort of set us up for the future. And we aren't really using anything but storage buffers for now anyway, so I think we'll just write really simple code here, and then we'll extend this over time to reflect things that we care about. The reason why I say this is because now if we make this really simplified assumption, we can just parse this stuff, or rather, not this stuff, hold on, somewhere, Oh yeah, yeah, right. Yes, yes, yes. So basically, we can parse these declarations, these two, out, and then just for now assume that they refer to a storage buffer, and it's possible to correct this later, but we just don't really have time today. So maybe we'll come back to this tomorrow. But for now, we can do this. So for now, let's do this. Let's create a struct for resource that we will fill later, and yeah. So this will have, let's see, so I want a SPIRV ID, which could be 0. You know what? Yeah, whatever. Basically, I want binding, I want set index, and I want bool valid, and then yeah, let's do ID binding set. What declares a resource, I wonder? Oh yeah, there's op variable, I think, or something like that. Let's look at our vertex shader. And then see what we want to be parsing out. So basically, I want to say in this case, I think this ID 16, which is that SPIRV ID I was referring to before, is the storage buffer with the binding 0 descriptor set 0. So it has two decorations which define where it's bound and things like that, right? But it's actually defined here, unfortunately, using an op variable statement. So yeah, so what we want is to say that we can have a variable that can be valid or not, and then it has a binding and a set, and then we'll just assume that everything is a variable, so we'll have a vector of variables, and we'll initialize it. We'll create one for every possible ID in a SPIRV, which is what this thing is useful for. So then when we have SPV op decorate, we'll have to parse this out. So I think probably what happens is there is ID, which is the first parameter, and then the second parameter is the type of decoration, and then the third one is the actual like value, right? So oh, by the way, we should assert here that word count is at least 2, one for the header and one for the thing that we are reading, and here we'll assert that word count is at least 4, and then we'll have like decoration, like deck kind, I guess. I don't know what these things are really called, and deck val. So this is 1, 2, 3, and then we'll switch on deck kind, and then if it's PV decoration descriptor set, assert ID is less than ID bound, then we'll just say that the variables set is the value, and then if it's binding, then we'll say that the binding is the value, and that's it. So I think that's how it should work. And then when we have a variable, then we will just say that, I guess we'll only need, yeah, that. Like you can see how there is 4,000 lines in this other program, in this other library, because it has to parse every possible thing out. And then we'll just say that if it's a variable, then it's a variable, right? Maybe this should really be like ID data, and then this should be variable, and that would be nicer. Or actually, it could be enum kind unknown variable kind. Let's do this. What does it want from me? Oh, right. So yeah, let's just parse things in a generic fashion, because we might need types later or something. I don't know what we'll need. Oops. And then here, this is ID variable, and we'll assert that this is kind ID unknown. Unknown is 0, so this default initializes, but let's just do this. Yeah, so that might be it. And now, the only issue is we don't know So when you declare a variable, there's this third thing. So there's an ID, and also, there's an ID, there is the type, and then there is the sort of class, or I don't know how these things are called in SPIRV. Let's see. And it has a value called uniform. So I want to storage class is what it's called. So I want to do storage. I want to store storage class, and then yeah, SPV storage class. It doesn't matter what it initializes to, probably, because in fact, let's just zero initialize everything, and then hopefully nothing blows up too badly, except for this guy. So the reason why I did this is that, so I think this next one is type, and I think this other one is storage class. And I want to do storage class. All right. And I mean, we might as well store type, because we will need type later to figure out if it's actually a if it's actually a storage buffer. So let's just, let's just do this. And so we now need 4. I don't know if decorations always have 1 like value, but if there are decorations that have more than 1, that it will be more convenient to say if it's this kind of decoration, we need to parse more data. So yeah, let's do it like this. And now let's go over all IDs, and then if ID type is ID kind is ID variable, then let's break here, or yeah, and then see if the code that we wrote even works in any shape or form. So see, for some decorations, apparently, oh, no, yeah. What's this decoration? Instruction, decoration number 3. Buffer block. So for some decorations, apparently we don't actually have all of the data, right? So this assertion is wrong now. So we'll need to do it like this. In fact, in this case, it's probably exactly equal. Let's see if that works. All right, so that's better. So that's confusing. So this is saying that, what shader is this? The mesh shader. Oh, we are starting the parse from the most complicated shader there is. That's not great. So this is saying that we have parsed a variable 2 times. Oh. Wait, hold on. Let's see. So we have a variable declaration with arguments 10, 17, and 1. Oh, we messed it up. Oh. 10, 7, oh. So for variables, the ID is not this one, it's this one. Wow. And the type is this, I think. Yeah. Wow. And then the other thing is the storage class, which is one, which I think was input. What does it say here? Input, yeah. Okay. This is somewhat messed up, but okay. All right. Let's see. So we have a variable with the storage class 7. SPIRV storage class ID storage class. Why is it not defined? I thought it's interesting. Alright, Visual Studio Watch window is not cooperating, but 7 means function, right? So we have some function variable and we have some input variable. Okay, so now let's only look at storage class, PV storage class uniform. Uniform refers, I think, hopefully, to the inputs to the shader. Maybe, I don't actually know this. So there is one with binding 1 and set 0, and there's another one with binding 0, set 0. And there's another one with... Oh, this might be the next shader. Yes, okay. So there was only 2 variables with class uniform in the meshlet shader, which is correct because there's only 2 storage buffers. So maybe the code that we wrote is working correctly. And now let us just say, you know what, assert ID storage ID set is 0 for now. And we also assume that ID type refers to, because the way it works is, so if we look at this descriptor, wait, binding, so this is the variable that we are parsing, and then it has a type 74. 74 is a pointer to 73, and 73 is a struct. But the problem is that the fact that it's a storage buffer is like here. So we have to follow this chain through the pointer. So we have to say, hey, this is a variable. Its type is a pointer to 73, and 73 is a struct that actually is a buffer block, which maybe is how you tell that it's a storage buffer, or maybe there's some other way. But it will be hard for us to debug code like this because we don't currently use uniform buffers or images or anything like this, and all of them would go through the same path. So for now, let's just say to a storage buffer. Obviously, this will change later, and for now only handles set 0. And let's just say that storage buffer mask. Oops, storage buffer mask. And I guess we have like a 32-bit mask right now. And let's just record the fact that we use this guy here. And let's just assert that we don't have some crazy like overlap between bindings. Alright, so that should work. Alright. Now, the final step is that when we create all of these layouts, we will pass them both shaders for now. When we do task shaders tomorrow, we'll need to refactor this code. But for now, let's just pass basically 2 shaders everywhere where we were passing RTX enabled boolean. Oops. All right. Okay, here we will say, let's assume for now, and I think this is an assumption that we will keep in the future, that if there is a storage buffer number 0 in the vertex shader and number 0 in the fragment shader, then it's the same one, which is a good assumption which can be a good assumption for complicated reasons. So for now, let's just say that storage buffer mask is via storage buffer mask or fast storage buffer mask. And then let's just go through, all potential bits, and if storage buffer mask has this bit, then we know we use this in one of these shaders. So we need a binding for this. Descriptor set layout binding. We know that it refers to the binding like number I in a set, and then we know for now that the descriptor type is storage buffer. We'll change this later. For now, we don't support arrays, and here we can say that for stage flags we can start from 0 and then just, well, yeah, and then if vertex shader or mesh shader needs this bit, then we will add the stage to this flag, and then if the fragment shader does, we'll add this to the fragment shader. And in theory, this should correctly fill everything, and we don't need this hacks anymore. This needs really as an input like an array of shaders, and this should be a for loop, but for now this is good. And then we will need a code like this when we are building the update template, because it's basically the same thing. We are saying for everything that might be for everything that might be used in the shader, we are saying if it's needed by any shader, then we need a update template entry in this case, right? Update template entry. And then we need to fill this entry. We don't need to know here which stage it is used in. This is specified elsewhere. We don't need this code. What we need to be doing is we need to say, oh, did I forget to, yeah, of course I did. Set bindings pushback binding. And here entries pushback entries. So, so the destination index is number I. Here's what we are saying. So let's say you have a shader that has as an input only 0 and 2. So it doesn't use binding number 1. We are still saying that we will want to pass an array where binding 0 is number 0 in this array and binding 2 is number 2 in this array. So here we are saying that the offset is matching the index of the binding, so we don't compact bindings automatically, which is nice because if you stop using a binding 1 in the shader, you don't have to change C++ code because binding 2 still refers to index 2. So that's nice. And yeah, so this will change in the future, but otherwise this is it, hopefully. So yes, so maybe this works. And then of course we need to change the code to, so here we are using the vertex shader. And here we are using the meshlet shader. All right. Our code worked. Let's check that it actually did. I mean, the only fragile piece of code is basically this stage assignment. So we can see this is the vertex shader, I believe. Yeah, so it has the stage flags as 1, which is vertex, and this is update template, which calls the same thing. We are creating a set layout twice now. We probably should not be doing that. That we can clean that up later. Yeah, okay. And here we are creating the RTX thing. Yeah, and stage flags is 128, which probably means mesh shader. So it looks like things work. So now we can parse out binding information out of SPIRV. We're currently assuming that we only support storage buffers, but it's hard for us to test anything else anyway. So it's a fine assumption. We will fix it later when we start using anything but storage buffers. And we now can like pass an extra buffer to a shader without changing this code. We will only need to change the shader itself. And the only other thing is we would need to change this code, right? For example, let's prove that things work. Let's try to prove that things work. So let's enable debugging in the meshlet path so that our kitten is nice. So let's say we wanted to move the meshlet buffer to index number 2. Right now, if we launch this, nothing will work. Let's see what will break. Something inside the OpenGL driver breaks. We disabled. There is an insufficient. This is the case where there's incomplete validation, etc. But the other thing that we want to change in this case is we are passing 2 buffers, and now we are saying we want to pass 3 descriptors where the number 0 and number 2 is a buffer, and the middle one we don't really care about. So let's just say that it's like a nothing, which we don't support the construction of. But let's just add it, and things should work, right? So it's now much simpler for us to change inputs to our shader because we automatically infer everything that we can, everything that we need rather, from the SPIRV blob. So this is nice. This makes our code more robust in the future. Alright, yeah, so this is the big thing that I wanted to do today. We were kind of fast and loose a bit about this thing because we didn't have too much time, but it's fine. If like at some point we'll rework this. but that makes me happy. This seems good to me. So yeah, that's kind of all I wanted to do. We can make one small refactoring to this code later, where we are passing the same shader objects to like a billion functions, and realistically we always need a layout, a template. We are creating the layout twice here. Let's we also need this layout for update template. This is redundant. And then here we will say for pipeline layout, this is redundant. This is especially redundant. I don't even know why this API works like this, honestly, because you have to pass in the layout. And I guess it doesn't have to be the exact same layout. Do we need to fill this guy, or can we just not fill this guy and have the thing work? Let's see. Yeah, you have to set it. Well, why would this ever be null? Oh. So you are saying we don't need this? Oh. Okay. Okay. Never mind. For push, we don't. This feels redundant because the layout has this data, so I guess we don't need this. Okay. All right. Yeah. So this is good. So basically, we don't really have much to clean up here. This code is pretty good. The only annoyance is right now to initialize the shader. We need to do three things. Well, we need to load the shaders, but that's kind of a given. And there's this assert thingy that's weird, but but that is easy for us to fix. The only annoyance really is that you have to create a layout and create an update template, and then also create a graphics pipeline, right? So there's like three things that you need to do to actually use, to actually start to render, which we can clean up later. Maybe we will, maybe we won't next time. Alright, yeah, that's kind of it. If you guys have any questions, I'm happy to answer them. If you don't have any questions, then it's been almost 2.5 hours, and we can end the stream. We went it's slightly longer than usual, but I guess the usual stream is like 2:20, so 2:30, 2:20 doesn't make much of a difference. Oh, and we need to do a very important thing. We need to cross. We did this. This is exactly what I planned to do. We still have this, but it looks like moving swap chain code out requires slightly more thought. Maybe, or maybe not. And then moving device out, we didn't do, but that should be simple. But we did most things that we wanted to, and we did update templates, which I initially didn't plan on. But yesterday I was thinking about this and I thought, man, if only I had an update template created, the calling code could be so nice. And now it is really nice, right? Like, and remember, we haven't written any weird wrappers around Vulkan or anything yet. I mean, we have functions that create shaders and stuff like that, but this is pure Vulkan code. This thing is just a constructor for union, right? The only reason we need this is because in C++ it's not super convenient to construct this union in a readable fashion. That's it. So this is pure Vulkan code otherwise, which is nice. And there's no weird like the only in debug basically there will be a call to this constructor, but that's it. So that's cool. And that makes me happy. Now this code looks way less scary than it used to, right? This is the draw call. This is the draw call, right? It's pretty good. All right. Enough adventure for today. Yeah, that's what I thought. All right, thank you everyone. 2:30, it's a good time to cut the stream off. And we are streaming again tomorrow, where we'll explore task shaders and hopefully don't run into any more bugs with validation. All right, thank you. See you tomorrow.